Hey guys, Mr. Betts here. I want to talk about some ideas that are going to lead into the second half of calculus. So, if you remember, we've been talking about derivatives, which were motivated by what I called the tangent line problem. So, we had a function, we wanted to find the slope of a tangent line to some curve at some point. And then in application problems, we interpreted the slope of the tangent line as an instantaneous rate of change. So it tells us how fast something's changing. So those derivatives and what we call differential calculus kind of make up the first half of calculus. The second half of calculus is motivated by what's called the area problem. And so this is something that we talked about really early on in the year, and we're going to come back to it now, and that's going to kind of drive the rest of what we talk about in calculus. And so I want to start this discussion here with a pretty simple problem. We're driving our car down the road. We're driving 60 miles per hour with the cruise control set, so it's staying a constant 60 miles per hour. We want to know how far we've driven after 2 hours. Well, this 60 miles per hour here is a special value. It's what's called a rate, and a rate is just it's a ratio, but it's specifically a ratio where we compare quantities with two different units. So we go 60 miles in 1 hour. So this rate is telling us that every hour that we drive, we're going to go 60 miles. So if we know that we go for 2 hours, we can multiply this rate by a time. And what happens here when we multiply by time is that the time units are going to end up canceling each other out, and we get 120 miles. So in this sort of problem here, what we have is a rate that we multiply by a time. And in this case, we get a distance. This may be a physics formula that you may recognize. In calculus, we're going to generalize it a little bit because we're not always going to be talking about motion. So we're going to say rate times time equals change. Now, this 120 miles, you may not think of that as a change, but technically that tells us how much our position changed over the 2 hours. So it's the distance between our starting point and our ending point. So it gives us a change. Now, if we look at this problem on a coordinate plane, we have this rate graphed with respect to time. What we're actually asking here can be interpreted geometrically as the area of this rectangle right here. So the height of the rectangle is our 60 miles per hour. The width of the rectangle is 2 hours. And when we find the area of that rectangle, 60 miles per hour times 2 hours. Okay, so we have the height of the rectangle times the base of the rectangle, or the width of the rectangle. We get that same answer that we got before, 120 miles, which tells us how far we drove over that 2 hour time interval. This is a pretty straightforward problem because we're driving a constant speed. Realistically, in real life, even if we have cruise control set, our speed's probably going to look more like this. It's going to fluctuate a little bit when we're going up and down hills and whatever else might cause us to speed up and slow down. But the area here that's between that curve and the x-axis is still going to represent the distance that we traveled over that time interval. And that's going to be the case whether the function looks like a horizontal line or looks something like this. So if it looks like this area here still represents a distance. So we're talking about a velocity graphed with respect to time. And when we find an area, we're getting a change in position, which is measured in miles. We might see this with other types of graphs. So kilowatts measure the rate that electricity is used or produced. If you're producing electricity, say with a solar array or wind turbine or something, hours would be the time units. And so this area here would represent an amount of electricity in what's called kilowatt hours. And that represents a total amount of electricity. We might see a rate like gallons per minute, which might represent how fast water is flowing into a tank. And again, if we know that how fast water is flowing into a tank given by this graph, the area here is going to tell us how much water flowed into the tank over the time interval. Now, I want to emphasize this accumulation of change thing here. Over any time interval, we can find an area that tells us how much it changed over that time interval. So over a 15-minute interval, we can figure out, it looks like for 15 minutes, it's flowing about 30 gallons per minute. So that's going to be about 7.5 gallons that get put into this tank. And then we can figure out over any time interval, whether it's the entire time interval or 15-minute intervals or 5-minute intervals, we can figure out how much water flowed into the tank by looking at an area. I also want to emphasize that it's a change because we might have a tank that has 100 gallons to start. So after 15 minutes, when our 7.5 or a little over 7.5, because our function's a little higher here, gallons enter the tank, now we're going to have a total of 107 or some such close number. So that area that we're getting here is telling us how much the volume is changing, not necessarily the total volume. And that's an important idea here. So big idea number one, leading into the area problem and what's called integral calculus, is that the area under a rate of change curve represents accumulated change. So in this example, the area underneath the rate of change of the flow of water gives us how much water flows into a tank or whatever this is measuring. Second idea here is that sometimes we have graphs that are pretty easy to work with in terms of area. So we have a graph here as opposed to this one where we can't really find the area exactly knowing geometry as we learned it freshman or sophomore year. But we have an area here where we can actually calculate it exactly. I can use geometric figures here. I could actually treat this as a trapezoid because this side here is parallel to this side. Or I could treat it as a rectangle and a triangle. Regardless of how I do it, area here is base is 2, and I'm going to keep units on here. Base is 2 minutes times the height. The height of this rectangle is 30 gallons per minute divided by 2. So the area here is 30 gallons. Weird to say area is gallons, but that's how it's represented in this coordinate plane. Area here is 2 minutes. That's the width of the rectangle times the height of the rectangle is 30 gallons per minute. And that's 60 gallons. So in total, that area here is going to be 90 gallons. And so we can find that area exactly knowing some geometry. Now that doesn't always work. Like I mentioned in the last example, we have what looks like a parabola here. We can't use simple geometric area formulas to find that area. So second big idea is sometimes we can use geometry to calculate the accumulation of change because accumulation of change is represented as area. Another thing that I want to talk about here is all of the graphs we've looked at so far, including this one, our rate function is above the time axis. So what that means is this area here that we get is a positive area, just like in geometry, all areas are positive. And we get a positive change. So over this time interval, whatever that area is, when we're looking at gallons per minute times minutes, we're getting a number of gallons that have been added to some quantity. However, if our rate is negative, this means that in this case, maybe water's flowing out of a tank instead of flowing into a tank. So the overall quantity now is going to be decreasing instead of increasing. So this area right here, even though geometrically we always consider area to be positive, we're going to call that area negative because the height, okay, let's just imagine this is just a rectangle right now. This height here we're going to call negative 10 instead of positive 10. So we can have negative area representations in the coordinate plane in analytic geometry. And so where we have positive rates of change, like we do here and here, we're going to have positive change overall. Where we have negative rates of change, like we have here, we're going to have negative change overall. Now, I know this sounds like a fairly straightforward idea. On this interval, water's flowing into the tank, so there's going to be more at the end than there is at the beginning. On this interval right here, water's flowing out of the tank, so there's going to be less at the end than at the beginning. But it is a really important big idea that if a rate of change is positive over some interval, then the accumulated change is positive. And vice versa. If the rate of change is negative over some interval, then the accumulated change is negative. So we have an overall quantity that's going up with a positive rate of change or down with a negative rate of change. One more idea that I want to talk about here, and that's going to have to do with something I've really talked about already. When we found this area here before, we got not just an area of 90, but we also included units and said that's going to be in gallons. Well, the reason is geometrically, when we're finding areas, we are multiplying lengths, and in the coordinate plane, those lengths have units. Horizontally, that's going to be minutes, and vertically, that's going to be gallons per minute. So the areas that we get units that are being multiplied. So big idea number 4, as we move into the area problem, is that the units of an accumulated change, which is represented as an area, are going to be horizontal units multiplied by vertical units. You can think of this as just like finding an area of a rectangle. Rectangles are going to be the simplest shapes to work with. In fact, we're going to use lots of rectangles for finding areas. And when we find the area of a rectangle, it's going to be base times height. Well, the base is going to have units and the height is going to have units. This is going to be our rate. This is going to be our time. And so the time units times the rate units will give us the units on our area, which is the units for our accumulated change. So here are all 4 of those big ideas all in one place. Some of them are pretty straightforward. Some of them are kind of a natural extension of things that we already know. But this is going to be the foundation of all of what we do with integral calculus and the area problem.